everybody. My name is Nicholas Crosby, and I'm the chairman of PIANC Working Group WG197. And we are now going to make a little presentation this afternoon on the work of WG197, now that the guide has been completed. So first, I'm just going to give you a little introduction to the working group. So the working group was set up in 2017 to produce a guide specific to navigation and to hydropower on inland navigations. There are actually many guides around to hydropower, both small and large, but PIANC, in their wisdom, realized that none of these guides address the specific issues associated with navigation and hydropower. PIANC also recognized that there were a lot of navigation authorities who had shown much innovation in developing hydropower and wanted to collect all this information together as a best practice guide. The members of the group were drawn from navigation operators, from consulting engineers and academic institutions to bring a wide range of experience to the group. The scope of WG197 was fairly tightly drawn by in the initial terms of reference. We were limited to developing hydropower on existing navigations. The large-scale schemes were excluded from our work. We were also excluded from tidal waters and estuary waters. During the work of the group, we visited existing navigation hydropower plants in Belgium, Holland, France, and Britain. And the working group actually presented a number of papers, a total of 3. We presented 2 in Panama in 2018 and 1 in Lyon in 2019. So the program for this webinar today, we're going to have 3 short presentations, which will take about 15 minutes each from 3 of the members of WG197. And we're going to present the highlights of the guide on some of the most important areas, hopefully whetting your appetite to go and read the guide and take some more information from it. And the final presentation is one based from on actual experience of developing hydropower on navigations from Ian White in the UK. There will be time for questions at the end of the full presentation. So if you want to submit your questions through the chats, they will be all collected together, and then they will be given back to the moderator, and hopefully we'll be able to answer them as we go. So what I would like to do now is to introduce the first presentation, which is from Sebastian, which will look at site identification and energy production.
Thank you very much, Nick. So we'll just wait for my presentation. So I'm Sebastian Erpicom from Liège University, where I am associate professor in hydraulics and hydraulic structures. And I will so speak to you about site identification and energy production potential, as Nick already told. So first, a few definitions. And so what is a hydropower plant in general? It is a converter of flowing water energy. And in natural conditions, flow energy is dissipated in river through turbulence and friction along the riverbed. And in a hydropower plant, we convert this flow energy to something else. So first into mechanical energy with a turbine, and then in electricity with a generator. So if you want to build or to set up a hydropower plant, first we need to assess how much energy we can convert from the flow. And so we need to find a place where we have enough energy to convert it. So let's have a look to the picture on the screen. What do we need to produce electricity from flow energy? We need a water level difference, what we call a head, H. And we need water going through this head, so we need a discharge. And as far as you have a head somewhere and a discharge through this head, you have a flow power, which is dissipated by the flow. And this flow power is simply the product of the discharge times the head and a few constants, so water density and gravity acceleration. And as far as this head and this discharge are available along time, you have energy which is dissipated, and the amount of energy is simply the product of the power times the time with power is available. So for instance, if you have a 10 cubic meter per second discharge somewhere crossing a head of 4 meters, you have a power which is dissipated by the flow of 400 kilowatts. And if your discharge on your head remain constant for 1 hour, for instance, the amount of energy which is dissipated is 400 kilowatt hour. And with a power plant, so you will build something to convert with flow energy into electricity, and with typical schemes today for small hydropower systems, so the one we will talk to you today, they have an efficiency around 70 to 90% typically. So if you have this 400 kilowatt hour flow energy dissipated somewhere, you would be able to recover between 280 or 360 kilowatt hour of electricity from this flow energy with your hydropower plant. Okay, so after these small definitions, let's start with site identification. So we'll come back to our navigable water courses, where we have requirements for minimum water depth to enable navigation. And to fulfill these requirements for minimum water depth, we usually build locks. So in fact, we create free surface elevation variations. So we create head in navigation water course to enable navigation. In these water courses, we also have discharge because we need some discharge to operate the locks, so to fill in the chambers of the locks, for also environmental requirements. And sometimes we have too much discharge available, and this discharge is released using weirs close by the locks, for instance. And so you can see in some navigable systems, we have heads and we have discharge available. And let's differentiate now two cases, the case of navigable rivers and later on the case of navigable canals. So in navigable rivers, we have weirs and locks that create heads, and this head may vary a long time depending on the discharge. So for instance, here on the two drawings, you have typical longitudinal profile of a navigable river, where we have locks and weirs, and the weirs can be active or fixed. That creates the conditions to enable navigation, so that control the water depth along the river to have enough water depth for navigation. And we have so these heads, so with water level differences at each weirs and locks. At least in, I would say, normal water level conditions, so in the plain lines, plain blue lines on the drawings. And in case of large discharges, so in case of floods, you can see that depending on the weir operation, in particular if it is active, but it is also the case when it is fixed, depending on the water level variation on the weirs to enable the flood passage, or the discharge passage, and the backwater curves development along the river, you can see your head, so the water level differences from side to side of the locks will vary, and we will see later, usually will decrease. Anyway, in principle, in navigable rivers, we have this head. And so now we have a different possibility to build this hydropower plant on rivers. And these arrangements depend on what we need to be able to do with discharge, in particular during floods, and navigation constraints, in particular regarding velocity in the river close by to the locks. So let's consider, for instance, what we would say typical layout in a river. We will have the power plant, which will be built aside the river cross-section, so on the bank, and usually in the opposite banks regarding the one where you have the locks. So why? Because like this, you will divert most of the discharge, and so most of the flow velocity to the power plant, so to the bank opposite to the one where you have the locks, and so you will have less flow velocity, or at least less important flow velocity to the locks, and so better navigation condition for the ships. So this is a typical arrangement of a lock plus weir plus hydropower plant system on a navigable river. Sometimes, if you have several, I would say, way of passage for the water or several branches in your river, you can dedicate one path to the lock. So one path will be dedicated to navigation only with low flow velocity, because you will have very limited discharge, only the discharge needed to operate the lock. And all the remaining discharge will be diverted to another path where you will have the weir to control the water level, and you will build your power plant close to the weir or on the weir if you have no space available to divert all the discharge, which will not be used by the locks, to this second part of the river. So another typical arrangement. And the last one, when you don't have a lot of space, and so where all the space in your riverbed is used by the locks and the weir which have to be built in your system to enable navigation, you can still build something to recover for energy with a power plant. And in this case, you will build your power plant on the weir and maybe make it movable just to be able to maintain the full discharge capacity of your river cross-section by moving the hydropower plant out of the water and going back to the initial state, I would say, without any obstacle in the river, in particular when your weir is active, and so when your weir can also be moved during a flood. Okay, so this was for rivers where we have heads and discharge available. In navigable canals, it's a little bit different. We still have locks, and so we still have creation of heads thanks to these locks. But usually we have no weir. Why? Because we have no discharge issue, no flood issue in a canal. And in particular, in most of the canals, we even have not enough water supplying to the upper part of the system, even to operate locks. So sometimes you need to pump water in canals to be able to operate locks. In this case, for sure, we have no discharge available for hydropower generation, and so no way to build a hydropower plant. But in some cases, in some specific cases, we may have discharge available, excess discharge may be available in the canals, sometimes during only certain periods of the year. And if you have discharge available, and if you have more discharge than the one needed to operate your locks, you can produce electricity with this discharge and a hydropower plant. So if we look to the drawings here, for instance, it shows you that depending on the discharge which can be diverted to your canal, if you have more discharge than the one necessary to operate the locks, and it's not only a question of instantaneous discharge, it's a question of volume of water available. So if you have more water entering your system than the one needed to operate the locks, you can use part of this water, part of this discharge to produce electricity. And so another way to look at this energy production potential, instead of looking at instantaneous discharges and heads, is to look to what we call a flow duration curve. And so it is another way to look at the discharge available in a river. And so in such a graph, you build this curve, which shows you how much discharge is available a long time in your systems. And for instance, you can see you have 100% of the time very low discharge, which is always available, and higher the discharge in your system, shorter the time it is available in your river or in your canal. And from such a curve, it's very easy to see what is needed for environmental constraints, or what is the environmental flow I always need for these environmental constraints. What is the discharge I need to operate my locks? So what is the discharge needed for navigation? And so what is the remaining discharge available a long time in my river to produce energy? And so I can start to decide what I will build as a hydropower plant, and in particular, will I build something to use a small discharge during very long period? So a power plant with a low output, so low power, but a high load factor, power plant which operate during long period to produce electricity, a small amount of electricity during long periods. Or maybe you would like to choose a larger machine, so with a higher power which will be generated, but for sure during smaller periods with a lower load factor. So this is for the discharge availability. We should not forget that we also need a head to create electricity from hydropower. So we also have to look at head variations, and in particular in navigable rivers during floods. So when the weirs, if they're active, are opened, the water level difference from upstream to downstream decrease. And so again, this can be assessed on something like a flow duration curve. It is our level duration curves, which shows you for each discharge what is the head, and what is the upstream level, what is the downstream level, and so what is the remaining head at your system. And in particular, the higher the discharge, usually, the smaller the water level difference, which is available to recover energy to produce electricity. And so if you combine everything on a single graph, you can see here in blue what is the discharge available in your navigable system for hydropower, so the discharge which will not be used for navigation. What is the gross head available, so what is the water level difference from upstream to downstream in green, and the product of both curves gives you the range of power which can be produced with, on the left, a power which will decrease because of decrease in head, and on the right, power which will decrease because of a decrease in discharge availability. Okay, so that's it for me. I hope I was clear enough. And so Nick, I give you the floor back. Thank you.
Thank you very much, Sebastian. The next presentation, we're going to actually look at the turbine technology that is typically employed on navigations where we install small hydropower. One of the most important things that the working group did was to set the limits on the ranges of head and flows that we should consider. One of the reasons is that the hydropower has a huge potential range of head and flow and a huge range of power outputs. So it was very, very important to limit it to the specific technologies and the specific sizes that we're likely to encounter. So in doing that, we realized that the likely range of head was from 1.5 meters to 15 meters, and a range of turbine outputs from 100 kilowatts to 10 megawatts. And this would cover pretty much everything we were likely to come across at the potential sites on existing inland navigations. These figures are quite small compared to some of the schemes, such as the River Rhone in France, or the Danube, or indeed the big rivers in America. But they're a different scale of development, and we were looking at retrofitting power plants to existing navigations. The two main turbine technologies that come out of that limited range are Kaplan turbines. Kaplan turbines are pretty much like a propeller, in that they're an axial flow machines, but they do tend to have variable pitch runner blades and guide vanes, which gives them a very wide range of efficiency. There are variants on the Kaplan. We have a semi-Kaplan, which has variable pitch runner blades and fixed guide vanes, and a propeller, which has fixed runner blades and fixed guide vanes as well. The propeller turbine has a much less wide range of high efficiency. We can arrange these turbines with a vertical shaft, or we can arrange them with a horizontal shaft. In larger sizes, they tend to have a vertical shaft orientation, and in horizontal shaft orientation, they tend to be smaller, and typically they are known as a bulb, a pit, or an S configuration. The second type of turbine that has come to prominence in the development with navigations is the Archimedean screw turbine. So the next slide gives you an idea of the range of applicability of these turbines. Okay, so this graph appears in the WG197 guide. So if you look at the graph, you'll see that what we've plotted is, on the left-hand axis is the head in meters. So it goes from 1 meter up to 15 meters. And then the discharge along the bottom, which goes from around about 1 cubic meter to 1,000 cubic meters. And that's a logarithmic scale on the bottom. So this fits in with what Sebastian was talking about, when you have a discharge in the head, if you put your discharge and your head onto this curve, it will tell you which type of turbine you need to look at. And to be honest, most of the turbines that we looked at and most of the developments were on the middle section of that graph, where we have horizontal Kaplan S or pit configuration, the Archimedean screw, or something called the Vlh turbine, which is a very low head turbine, which has been specifically designed for such applications. If you go further to the right, we're talking about vertical Kaplans and bulb Kaplan turbines. These tend to be much bigger, much larger turbines, which you typically find on the larger developments on rivers. So those are the range of turbines that we actually looked at and concentrated on. And if we now go on to just have a quick look at some pictures of some of these, just have you an idea about what they look like. Okay, the first one is the VLH turbine. This was developed specifically for low head applications. Normally, you wouldn't look much below 3 meters in conventional hydropower because the head is quite low and it's difficult to extract energy efficiently from these. But this turbine was designed specifically for such applications, making use of all the modern technologies that we have available now. And its range is 1.5 to 4.5 meters, which covers a lot of locks on navigable rivers. The power rating is 500 to 600 kilowatts. The runner blades have a variable pitch, and the generator is a DC generator, so it can run at different speeds. And by combining the variable pitch runner blades and the DC generator at different speeds, you can get a lot of variation in flow and with keeping your high efficiency. The other interesting thing about it is it has its own built-in trash screen, which is the curved wiper that you can see. And it's actually fish-friendly by design. One of the main criteria for designing this turbine was to make it fish-friendly, so that fish can pass through the turbine without injury. And that makes your trash screens upstream and downstream much more simple to deal with, which is what the next presentation will cover. So if we actually just go on and have a quick look at what that looks like in a configuration. There you go. This is an installation on VNF in the River Meuse, and this is actually Saint-Joseph Lock. And what the project here, the existing stake weir was replaced by a rubber inflatable weir, and on the left side of the picture, two VLH turbines, two 500 kilowatt VLH turbines were installed in this overall development. So this combines an active weir with the turbines, and I'll talk a little bit about that later. The next type of turbine is the bulb, is a pit turbine, and that person standing in front gives you an idea of the scale. This is a full Kaplan, so it has movable guide vanes and movable runner blades, and the water, when it's installed, flows around the outside of the cylinder, and inside the cylinder, behind the gentleman standing in front of it, is where the power is taken off and taken to a generator. Either the generator is located in that pit, or there's a mechanical transmission to bring the power out of the pit to generator above. So that's a pit type turbine, full Kaplan. And the last one we'll have a quick look at is an Archimedean screw. There's an Archimedean screw turbine. The head limit is limited to 10 meters and 600 kilowatts output, and that's limited by the physical size of what you can actually make as a screw. So by the time you've fabricated and transported it, you need to that limits what you can do with an Archimedean screw. One of the reasons they're used a lot is they're regarded as being fish friendly, because the water surface within the turbine is always open to atmosphere. So you don't get large pressure changes within an Archimedean screw that you do within the other types of turbines. They also can be used as a pump, and there are a couple of installations where on canals rather than rivers, where these are actually used as pumps during the periods of low flow. But when there is excess water, as Sebastian indicated earlier, these can actually be reversed and used to generate energy. So they are dual purpose. The next, what I want to talk about a little bit more is one of the things that have to be considered which is the interaction of the hydropower plant with the navigation. Obviously, navigation levels are controlled within strict limits. Quite often you find that there are laws and regulations and bylaws which give you the range of water levels that you can vary by for the aid of navigation. If you remember that navigations are set up to move vessels around, so the control of the depth of water over obstacles is very, very important. Levels are controlled by weirs, and they can be passive or fixed or active with automatic moving elements. The sizing of the weirs, both the passive and active ones, has been done to maintain the navigation levels in normal circumstances. Obviously, when you're into floods, you're potentially stopping navigation and the water levels do what they have to do to discharge the flood water. Now, if you introduce generation, which takes flow away from the existing weirs, it puts additional factors into the governing of the navigation levels. If you've got active weirs, the turbines and the active weirs, they must be integrated in such a way that the set points of level that the weir operates to and the set points of level which the turbine operates to, they must be integrated so the two things don't fight against each other. It's the turbine and the active weir must be integrated in the design. We now move on to next slide, if it's coming. Yeah, there we are. So when you've decided how much water you want to take through your turbine, the crucial thing to think about is the startup and shutdown of the turbine. There are two approaches that you can take. If you limit the flow through the turbine, such that changes don't affect the navigation level, the amount of water you take out of the river to put through the turbines is relatively small as a proportion. So when the flow changes through the turbines, it won't affect the navigation very much. Or the second alternative is you integrate the active weir and the turbine control system. This obviously allows you to take more water out of the river and therefore generate more power. So the two changes that you have with a turbine, you've got a startup, you've changed the load, and you have a normal shutdown. Now these can all be controlled by the turbine control system, and you can change these at such a slow rate that the sudden changes of flow don't lead to navigation level excursions. The biggest problem is the fact that with a turbine being an electrical generator which is connected to the grid, things beyond the control of that particular generating installation can cause the turbine to shut down immediately and quickly. And that, in that case, you then potentially get a large excursion of level. So what you need to do then is to do simulations to show how the levels vary. And this next couple of slides show some simulations. The first one is one with a passive weir on a 20-kilometer reach of river, where the turbine was taking 80% of the flow. So the graph shows here, what you've got there is how the water level upstream varies over time, and the time on the bottom is hours. So over a 24-hour period, the level rises because it's controlled by a passive weir, potentially by 75 centimeters, or almost 90 centimeters, which may well take you outside the bounds of your controlling river levels. And the river flow also takes a long time to recover back to where it was. If we look at what happens when you have an active weir with exactly the same parameters, you can see that the operation of the active weir can bring the water levels upstream and downstream and the river flow back into where they were before the operation of the power plant stopped, within a very much shorter space of time. So if you want to take a lot of water out of the river to generate more energy, you're going to have to put in some active control of the water level. You can't just rely on a weir, passive weir. And finally, what I'd just like to go on to one last slide is a picture of what can happen to the flow over a passive weir in this case. With a power plant before and after picture on the left and right. The power plant was constructed, and even though it doesn't take a large proportion of the flow, it's still altering the way the water flows over the weir and what happens downstream of the weir. Now, all of this can be modeled and looked at, and physical models and numerical models can be made to see how the introduction of a turbine can affect the navigation. And I do have one final slide, which is just a few conclusions just to give you. So there's several types of turbines: the Vlh turbine, the Archimedean screw, and the small horizontal shaft Kaplans and derivatives. The presence of small hydro can affect the maintenance of navigation levels. The effect on the navigation levels can be mitigated by reducing the proportion of water available or producing an active weir. And the hydro schemes, even at low proportions of tidal flow, can change the direction of flows with effects on sediment dispersals, erosion, and water velocities. So that shows you how we've gone from deciding how much power is available to what type of technology you might use to extract that power from the river, and other areas that you might need to consider when you're thinking about developing a small hydro scheme on your navigation. I'm now going to hand over to Austin, who's going to talk about trash racks, trash rakes, and fish passage. Thank you very much.
Thank you, Nick. Good afternoon. My name's Austin Flaver. I'm a director of ANF Consulting, who specialise in the design of low-head hydropower and, in addition, fish passage. I've been asked to present a brief paper on the subject alone of fish passage and trash racks or intake screens, and how they are incorporated into hydropower schemes. Now, the introduction of any physical structure into a watercourse, whether that be a river or a canal, introduces an obstruction to the natural movement of water, and by that, anything that may also be in that water. Such objects can be natural, such as the variety of fish species which colonise watercourses, or maybe just use them for the purposes of migration, or it can be debris which is carried along the watercourse, having inadvertently found its way in there. A well-designed hydropower installation will seek to minimise the impact of the installation on the natural movement of both. But by its very nature, hydropower plants often take large volumes of water, and they can naturally attract both fish and debris, causing problems for the operator of the hydro plant, and also, in the case of fish, for the fish themselves. To minimise this impact, hydropower plants are designed to incorporate both trash screens and fish passage measures so that the plant can operate effectively when it's not being impacted by debris, or indeed impacting upon the fish within the watercourse itself. These measures are what we term trash racks, or sometimes called intake screens, and fish passes. Now, the need to protect the turbine seems initially to be the most important one. After all, they are the heart of any hydropower plant, and they are expensive items. However, whether they actually need protecting from normal debris depends partly upon the type of turbine used. As Nick mentioned, Kaplan turbines are often used, and these have rotating runners comprising of 3 or sometimes 4 blades and spin at relatively high rotations, and impacting debris can cause damage, so protective screens would seem sensible, and indeed it is. Archimedean screws, though, however, rotate at much slower rates and have large pockets of water which pass along them. So these screws can actually transport large objects down them without damage to either the screw or to the objects themselves. So whilst very large objects, such as trees or indeed boats, shouldn't be allowed to pass down them, an overly fine intake screen actually can cause potential blockage issues, whilst trying to protect a screen from impact from debris which wouldn't actually cause a problem to the screw. So consequently for screw installations, we find wide-spaced bar screens are often used to minimise blockages that exclude very large objects. Now, stress screens, or more correctly, intake and outlet screens, are often required to keep fish out. And again, just which type of turbine is installed will determine the type and the nature of the screen which is used. Some are to deter deliberate entry of fish, and others are to deter unintentional entry. Salmon and sea trout are well known for their desire to move upstream during migration periods, and in doing so, they naturally follow the direction of flow within a watercourse. This causes them to move towards hydropower plants when approaching from downstream, as this is where most of the water is often coming from. Whilst no one has suggested that a mature salmon would inadvertently swim into a rotating turbine, the confusion that this blocked passage can cause the fish can create delay and wasted energy, which can reduce the chances of any one fish making it upstream to suitable breeding grounds and successfully breeding. Consequently, outlet screens are often required to prevent this wasted journey simply to visit a rotated turbine. Eels also migrate upstream, but given that they do so as juveniles, they are often much smaller and much less able to swim against strong currents than their salmoniid counterparts. Eels would not normally choose to swim up to a turbine, as the flow coming from it would be too strong. However, once they are past the weir or other obstructions such as a lock, they can come into close contact with the intake to a turbine, which, if not guarded, can pull them back into the turbine with the certainty of them ending up downstream of the weir, if not mortally wounded by their journey en route. Consequently, fan screens are often required on intakes to prevent eels being pulled into Kaplan turbines, though they're not usually required for screws, which can move eels downstream whether they want to or not, with a much lower risk of actually being harmed. But in building a hydropower plant, we unavoidably change the natural flow pattern of the watercourse. And in doing so, we change the natural direction which both debris and fish will travel, with both being drawn towards the turbine, along with at times the majority of the flow in the river. In the case shown above, the original flow pattern follows the blue arrow, but once the hydropower is built, the flow changes to the green arrows. And the debris, and in many cases the fish, follow this same change in flow path. It's important to remember that in the case of fish, movements can be in either direction, depending on the type of fish and the stage in that species' life cycle. All movements, however, are guided by the flow pattern within the river. It's only by understanding the behaviour of both fish and indeed of debris that as hydropower designers, we can design hydropower plants to ensure that fish are not delayed by confusion or blind alleys, and also that debris is kept away from the turbine and moved away by whatever means is mandated by local licensing authorities. So debris screens and trash screens and fish passages are interrelated and are not two separate elements of hydropower design. By correctly designing intakes and outlet screens, it is possible not only to deflect debris floating in a river, but also to change the behaviour of fish. The screen shows two blue stars, which are two particular areas where hydropower plants come into direct conflict with migrating fish of whatever species, either upstream or downstream of the turbines. The downstream star shows where upstream migrating fish who will be following the main flow in the river will come up against an outlet screen, which will block their entry to the turbine. The upstream blue star shows where the downstream migrators, which would include mature eels and juvenile salmons, they follow the pattern downstream and will come across an intake screen, which also will block their onward passage. By placing such screens at an angle to the flow, however, both upstream and downstream migrators can be guided along the screen using the flow to attract them, so that at the end of the screen is indeed the fish passage, which will then attract them and lead them safely past the hydropower plant. In the case shown, the yellow and orange arrows show the preferred routes for both upstream and downstream migrating fish, and the alignment of the fish pass with the upstream and downstream ends of the respective trash screens. Without such guidance, and at worst if fish encounter a barrier perpendicular to their travel, fish would end up confused and delayed whilst they try to find a route past the obstruction. For all migrating fish, time is of essence, so any fish passage must be designed so that fish will find it quickly and make passage without undue delay. Here's an example of how, in the case of a downstream exclusion screen, prevents upstream migrating fish from entering the turbine tail race, as the route is naturally blocked by the screen. But the natural movement of flow coming from the screen and from fish passage measures upstream naturally attracts the fish along the screen until eventually they locate the fish passage measures, which is their safe and speedy route past the hydroplant. And as hydroplant designers, this is the scenario we try to create to prevent this delay that migratory fish may experience. So fish passage is not a one solution fits all schemes. Different rivers have different fish populations, both resident fish and migratory species, and these have different movement behaviours. This even applies to fish which are not regarded as migratory, as even resident fish are known to move up and down a river at different times of year for a variety of reasons, which could include different feeding areas, different areas for breeding, and sometimes to avoid areas that have become overpopulated. Designing fish passage is therefore particularly sensitive to the location of the hydropower plant, and in the case of eels, particularly its proximity to the sea or the tidal limit of the river. In the UK, with its relatively short rivers, eels are generally considered as elvers for hydropower design, up to around 100 millimetres in length, whereas in continental rivers, often many hundreds of miles from the sea, they will be far larger, based on the simple principle that eels migrate upstream rather slowly over several years, and in doing so grow from the small glass eels that enter the river system to more mature eels that live further up the river. Intake screens therefore tend to have apertures determined by the size of eels rather than fish. And the size of the eel depends upon how far away from the navigational limit, from the tidal limit the screen actually is. But these can result in screens varying from between 3 and 30 millimetres of aperture. So whilst other fish often are present and need protecting, they are often larger than the size of the eels. So it is the eels that actually determine the size of the screen. Now, once the predominant fish species have been determined, the designer then looks at how to provide the best measures for that particular species of fish. And in the case of eels and fish, they are quite distinctly different. Eels seek low flow conditions. They're rather poor at swimming, but they are excellent crawlers. So eel passages tend to provide low flow volumes and media such as bossed tiles or bristles, along which the eels will actually crawl. This allows eel passes to be far steeper than fish passes could ever be, and in many cases they can be prefabricated. On larger rivers, these can sometimes be combined with fish passes, though there is still a need for some form of media for the eels to push against to aid their ascent. Fish passage is similarly designed for the predominant or the target fish species, and this choice is then often constrained by the preference of regulatory authorities in each individual country. Again, in the UK, there's a strong preference for Larinia type fish passes due to their multi-species suitability and their low blockage self-cleansing characteristics. But in other countries, other designs such as the vertical slot fish passes are preferred. Once again, we find that there is no one-stop shop for fish passage, and each must be tailored to the suitability of the site, to the river, and to the target fish species. As mentioned earlier, intake screens are trash racks determined by both the need to protect the turbine and to protect the fish. This leads to a large variety of different screens that may be required. And with that, the means of dealing with the trash or the debris which may inevitably collect on the screen. Clearly, very fine screens, such as those found on Kaplan turbines in the UK, can be as small as 3 millimetres, because they're designed to protect eels. But similarly, on larger rivers, they could be 25 to 100 millimetre apertures, where protection is primarily for the turbine rather than for the fish. But all river-based hydropower plants are faced with substantial volumes of debris during flood events, and any trash rack or intake screen, irrespective of its aperture, will block during such events. During very high flows, preventing damage to the turbine and the associated equipment is paramount. But at less intense flow events, maintaining generation is key, keeping the screen clear of debris so water can reach the turbine. This usually requires the deployment of an automated screen cleaning system. In some installations, an inclined screen isn't possible, and a perpendicular screen is installed, such as the one shown. These screens will collect significant accumulations of debris during a high flow river event, and these will require mechanized equipment to remove this debris due to the physical size and the volume of the debris which will be collected. To fail to remove such debris will restrict the power generation at best, but may actually jeopardize the structural integrity of the screen at worst. As a further matter, the debris which is collected in this manner often has to be disposed of by the operator of the power plant, usually at their own expense. Alternatively, some screens can be inclined to the flow. These are sometimes referred to as side offtakes. For these, they are often able to deflect the debris downstream, and where permitted, automated cleaning systems can, when combined with horizontally inclined screens, these can be designed to push debris downstream on a screen without actually removing it from the river. And this does not occur in the cost of disposal by the operator of the hydro plant. So fish passage and trash racks are not supplementary items which are bolted alongside a hydropower plant, but they are part of the whole. And when designed correctly, they will help ensure that the turbines are operated efficiently, safely, and without risk from impact damage. They'll also then ensure that the aquatic life within the river on which the power plant depends can move as freely as possible and not be adversely impacted by the renewable energy generation plant. Thank you. Back to Nick.
Good afternoon, everybody. I'm Ian White. I'm a consulting engineer that's for about the past 10 years has been working on the development of low-head hydro plants within the UK. And in that role, I've worked with Austin, the previous speaker, on a number of sites. What I want to talk today is about the background of UK river navigations, the contrast between, to a degree, the new build and the retrospective installation of hydro plants, which is what is happening in England. Why do it, how to do it, what to do, and most importantly, what not to do and what lessons can be learned. To quickly look at the future and then ask the question, has it been a success? And in the process of asking that, answer my original question, so what did win, hydropower or navigation? Within the UK, all of the hydro plants are basically built on the major river navigations to ensure that we get adequate flow to make them economically viable, as Sebastian was indicating in his presentation. So we tend to focus as to who had access to water rights. Suffice it to say, a lot of money used to change hands to achieve that. Post the Industrial Revolution, the big waterways were developed for freight transport to the estuarial ports, to carry coal, to carry fertilizer, to bring products backwards and forwards across the country. It has to be said that now little freight transport exists on the upper reaches of the rivers. It certainly still is there on the lower tidal reaches, but now these waterways are used significantly for leisure craft. And in a way that it's important to provide a use of them, but also it means that there are less experienced operators of the vessels, and you have to be that more careful in terms of how you manage flows, changes in water levels, and the such like. Many weirs are over 150 years old and are therefore classed as heritage structures and have special planning under special protection under planning legislation, which in itself can cause problems with regard to the initial concept of a hydro plant being approved, and then in the detail of constructing it. A legacy issue of all this development is that when the big weirs were built for navigational purposes, there was a lack of fish passage for migratory species. And this in turn has had a major impact on the migratory fish such as the salmonoids, the eels and the such like, attempting to move back upstream to spawn. And is something that featured significantly in the application of the EU's Water Framework Directive to see the improvement of waterways. We're also seeing the impact on water level, that the time of concentration for water to travel down the rivers has significantly shortened due to the level of upstream development taking place, and as somebody once said to me, concrete in the countryside. But now we're obviously seeing major changes being planned for as a result of climate change. Within the UK, there's been no national or regional plan for low-head hydropower generation. And all that has been done has been of a retrospective nature by constructing hydro plants alongside existing weirs. We have not had a programme with the economic drivers such as the Tennessee Valley or the Rhone to develop hydro plants, so they have never been an integrated part of our navigational structure. The UK traditionally has relied on using coal-fired power stations. This is mainly the result of us having a nationalised coal industry and thus government policy. And until relatively recently, in the last 20 years, there has been no incentive to change from coal to other sources. But obviously, with the interest in green energy, with climate change, with all of that we've seen being discussed in the last couple of weeks with COP26, there's been a worldwide move to looking at green energy. And certainly it's been the UK government's policy to support such initiatives, primarily with the feed-in tariff. This is a subsidy paid to owners and operators of green energy plants, whether it's solar panels, solar farms, wind turbines, and hydro plants as well. But another reason for doing it is the navigation authorities themselves under pressure to increase their income, especially those that are reliant on grant funding from governments. And so it has always been an opportunity to look at income generation from using its land, from using its assets, even if it's to permit the use of that differential head across its weirs. And certainly it's been seen as the need for a more integrated business, and thus it should use its assets. So how to do it? Well, I have to say, one of the things that impressed me about the working group was the paper that was produced and all its recommendations and advice. It has brought together a lot of experience from the last few years of work and is a very good document for helping people make up their minds that schemes can go forward. One of the key starting points is identifying potential sites and perhaps doing a hydrographic survey of the rivers. One of the conclusions that seems to have come about is that anything less than 100 kilowatt output is not worth doing in terms of the civils costs, land costs, access, grid connection, and the such like. One of the key expenses that we do see is the cost of a grid connection. And unless there is a 11 kV cable route in the immediate vicinity of a hydro plant, it can become very, very expensive to connect to the grid. An alternative to that is if you have an end user in the locality to whom you can sell the electricity to, but unfortunately, these are few and far between. You do have to look at the planning issues, whether it fits within local and national policies. And it has to be said that most planning authorities now try and encourage green generation. We've got the ecological issues. Are the rivers particularly critical? Are they very special? For instance, the River Severn has special characteristics, which seem to unfortunately have ruled out hydro development along its length. It is also the fluvial aspects of, as been described earlier, the need to pass flood water down to maintain low levels or maintain levels at low flows for navigation. And any other regulatory aspects, say from the English Environment Agency, from the local authorities, from ecological bodies like Natural England and the such like. But if you can tick those boxes, then certainly the navigation authorities can facilitate and support developers. I think it's fair to say that the navigation authorities are not in a position to invest directly in starting up schemes because it is outside of their day job, what they're used to. But there are a number of organisations, along with bankers, who are prepared to make the investment. So it is a question of getting the FIT authorisation is a good starting point. Will the scheme have the benefit of the subsidy from the UK government? This has been the driver on about the 12 schemes that I've worked on over the last 8 or 9 years. Unfortunately, the FIT funding stopped in March 2019. March 2020. But there are now other purchasing guarantees coming in that give confidence to investors that they will see a return on the their investment into the sites. We also have to see, and this has been part of my role when I've been working for the Canal and River Trust within England, and it was mentioned by Nick, you have got to protect the statutory function of the Navigation Authority by ensuring that at low flows, there is enough water left in the navigable channel for the safe passage of craft. So what to do? Well, there are physical surveys, both of the land and of the channel. And the channel is particularly critical. It has to be done, obviously, in 3D, a full bathymetric study to understand the implications of what can happen as you change the flow within the river, and as Austin demonstrated with his aerial photographs of how the bed can move from one side to the other. We have to look at the fishery implications. Is the riverbed going to change from, say, nice clean gravel to heavily contaminated silt that will stop spawning? As a result, do you get this form of pollution? Is the risk of sedimentation? And are you actually making whatever migratory fish passage already exists even worse? You have to do a navigational risk assessment to examine the channel velocities, whether there's going to be an ongoing dredging program because of downstream sedimentation. Could there be scour damage, which would cause collapse of the navigational structures? Sedimentation, are we going to see shoals building up across the outlet from the locks? And also about the public access, and that's public access in terms of people on the river and boating, people doing wild water swimming and the such like. Are they protected from the operation of the hydro plant? And even in terms of land-based access into it, that has to be carefully considered as well. So this is a site, you've seen the various shots of this photo earlier, but this is a good example of a 500 kilowatt site, flow from left to right heading downstream. The building on the left is actually the main switch room for the connection with the local grid. And this site was quite fortunate, as immediately upstream of the, to the left-hand side of the photo, was an 11 kV cable route crossing the river, and we could tap into it. But that said, a 3 kilometre long road had to be built to get access to the site and bring in all the construction equipment and all the plant, this turbine, etc., when it was required. So, beg your pardon. So, what not to do and what lessons have been learned? There is always the opportunity to cause conflict with other river users, and I've learned over the years, whatever you do causes conflict, either with anglers, boaters, or abstractors. Some of the issues we've talked about, like creating adverse operating conditions. For instance, a rapid shutdown. And this is a problem we've discovered on a couple of sites, is that when you have a power cut, certainly with the turbines, they have to shut down their output within seconds, and you can end up with a reflux wave traveling upstream. And when you're trying to stop, say, 66 tons of water flowing downstream in a matter of seconds, you can create quite a big wave. And one of the options we've looked at is perhaps even putting floating breakwaters in across the inlet to hydro plants to absorb a lot of that return wave if it should occur. Certainly draw into intakes can be a problem, especially with more small craft, if you've got canoeists, kayakers, and even low-powered leisure craft. So again, you've got to be careful how you handle that. Starting up can be a problem, but with the development of software and the such like, it's always possible to have very slow start. And when you have a planned stoppage, a planned shutdown, do that very slowly. So what about the future? Well, there are more sites to be developed. Some are in the pipeline and looking for funding. The question I would ask is, will these be financially viable compared to wind and solar generation? Are there green government subsidies available? Well, no, not so much subsidies now, but there does seem to be a move towards guarantees for the sale of electricity. I think one of the key things I've recognised over the years is the economies of scale, in that there unfortunately isn't such an economy with low-head hydro plants, as they are all unique and are not capable of mass production compared to, say, looking at solar panels or wind turbines. I also think there is an issue about comparative installation costs, such with hydro at about £3,300 per kilowatt, solar at 1,000, onshore wind at 1,200, offshore at 2,100. So there is an extra overcost in going the hydro plant route, but not to say it can't be done. So has it been a success? Well, certainly on the Canal and River Trust, there are 10 plants up and running with a mix of turbines and screws. Are they exporting electricity on a regular basis? Yes, they are. We're seeing increased biodiversity in that migratory fish are now returning because the fish passes have been installed as part and parcel of the hydro plant development. And I have to say, from a navigation authority's perspective, that is a significant financial benefit, as they are getting a fish pass for free. And I believe the investors are seeing a return on their investment in that the plants are being traded, they are being bought and sold. And that would not be happening if they were not showing a return. So to answer the question, who did win, navigation or hydro? Well, the navigation authorities benefited with income. Biodiversity is less investment needed for fish passes, better control of water levels, develop the green credential. The developers have generated both electricity and profits, and society gets green energy and increased biodiversity, so an improving environment. So I would suggest, to answer who did win, navigation or hydro, we all did. It was a win-win-win for all. So I would like to say thank you, but I would also particularly like to extend a thank you to the members of the working group under Nick's chairmanship, because I have to say, I believe it was a very worthwhile document and certainly has been of great benefit to me and to others when we have been looking at the development of low-head hydro plants on inland waterways. Thank you.
Okay, thank you very much, Ian, for that. Thank you also to Sebastian and Austin. As you probably realise, they were just the highlights of what's in the report and what's in the guidelines. There's a lot more information in there. We could probably spend all day going through it if you wanted to, but I don't think we have a very large audience for that exercise. So those 4 presentations will hopefully have whetted your appetite for exploring this in wider details. What I would like to suggest now is that we are going to have some questions and answers if anybody's got any questions, but I also know that Philip wants to do a presentation on InCom in general. So perhaps we'll ask Philip to do that now while the questions are coming in, and then we can finish off with any questions. I'm not sure if we have any questions yet.
Hi, Nick. My intention is mainly to try to promote a little bit PIANC activity, and especially inland navigation committee to the participants. So I will speak a little bit more general than the working group. So I think it would be better that you proceed to the questions first.
Okay.
Then I can make my short promotion if you think it's suitable. Thank you.
Well, we have the one question from you, Philip, concerning whether small hydro can be pumping at night and turbining during the day. That can be done, and in fact there is one installation I know of which is a tidal installation, and the pumping is actually not for the purposes of navigation. The pumping is actually for the purposes of running a canoe slalom during the day, and at night when the tide is out, the water then flows back through the same pumps to generate power during the the periods when it's not in use as a canoe slalom. The other case where there is a large amount of pumping and turbining is, of course, in Belgium, on the Albert Canal, where the owners of the Albert Canal, whose name I can't pronounce, I'm afraid, and who one of the members of the development team for that was on the on WG197. That's Jan Mangelschotz was part of our team, and he went through the development of how a hydro turbine generating station could also be used as a pumping station. I think one of the things that came out of Ian's presentation, which is something which I think is highlighted in the guide, is just how difficult it is to forecast what the regulatory regime or the development regime in any particular country is. The rules are not only different from each country, but they vary in time through in each individual country. And whilst we've given examples of how developers have worked in different countries, it's very difficult to say, yes, that's the development model that you have to follow, because the rules change, subsidies change, the direction of the government wants to go changes, whether you can get a subsidy for providing a fish pass, whether you can get a subsidy for your electricity generation. All of these things vary with time. So that's the most difficult aspect of this. The actual technicalities of building the plant and designing a plant are relatively straightforward compared to the regulatory environment, and that varies from country to country.
Thank you, Nick.
Maybe I can add just a word regarding the question by Philippe.
Yes, please, Sebastian.
So I think using navigable waterway to store electricity with pump storage is only a question of volume available to store water upstream of the system. So I think in most of the navigable rivers, as constraints on river levels are very strict, with only limited variation of water level which are possible, there is no large storage capacity regarding water upstream of the river, so no way to store a large amount of electricity. But what is done on the Albert Canal in Belgium, for instance, what is very interesting is to use machines which are able to be either pumps or turbines, and to use the machine as pumps during dry season to pump water back upstream. So in fact, to cancel the discharge consumption in the canal during dry season with the pumps, and on the contrary, during the wet seasons when more discharge is available upstream, for instance, in this case from the river which supplies the canal in water, to use a machine as turbines to produce electricity. So it's not really pump storage in the sense to store electricity, but more pump storage in the sense to have machine able to do both, and depending on discharge availability in the system, either to decrease water consumption by the logs or to produce electricity from excess discharge available in the system.
Nick, may I just add something to that? One of the things that I think we could see developed is the introduction of inflatable weir crests. There are only 2 in the UK that I'm aware of, but I know there's a lot in the US, a lot in Japan, and quite a few in Europe. But I think that would achieve several things, because in low flows, the weir crest could be raised and therefore increase the head across the hydro plant, which would be beneficial to the power output, obviously. But also that they could be set so, in fact, the permanent weir crest is lowered. So as we see the impact of climate change and the such like, faster flows coming down the river, then in fact the crest could be deflated and more water passed downstream. And in fact, that's what's being done with the 2 inflatable crests that are done in the UK, is they were more about flood protection and passing water through what were fixed weirs. but can now be altered but maintain an upstream level. But I think there is an opportunity there for the development of increased hydropower, even at some existing sites.
Okay, thank you, Ian. I think also the schemes that we looked at in France on the VNF in northern France on the Meuse River, they replaced existing stake weirs with inflatable rubber weirs. I think there were two things. One was the controllability of the stake weir. They're purely manual operation, and they're actually quite dangerous to deal with. Sending people out to remove these stakes on some quite long weirs and folding them down before floods. So the actual use of rubber weirs, inflatable weirs proved beneficial for both the hydropower, the maintenance of navigation levels, and passing floodwaters. Okay, well, as we don't seem to have much in the way of questions that have come in yet, I will pass over to Philip to give a presentation on the wider aspects of InCom. If any more questions do come in the next 10 minutes or so, we're quite prepared to stay and answer them. So if you've got any more questions, please submit them, and I'll hand over to Philip.
Okay, thank you. So I hope you see my screen. Do you?
Yes, Philip, we can see your screen.
Okay, so, oops. Yes, so my name is Philippe Rigaud. I am not a member of the working group on the small hydro. I am the chairman of InCom. So this presentation is more targeting the person who are not fully, I would say, involved and aware about the PIANC activities. So I apologize for the order, but anyway, it's nice to refresh your memory and to give you some new information. So InCom is in charge by PIANC to try to manage the activity related to waterways and especially to navigation. So our task is to create some working group as this one. And of course, I am very happy by the result of this report, and also the outcome of the working group, which is not only a report, but also this kind of seminar or webinar. So in the future, we will try to more generalize this kind of outcome for dissemination. So I would like to present you a series of working group that has published already their reports, and also some current working group that are working, and some future working group. So my aim, of course, is to attract you in order that you maybe read some reports, that you join some working group maybe, and for sure, if it's not the case, that you join PIANC. So I will not talk about this working group 197. It was a success, and thanks again to Nick and to all the working group members. So first, just mention quickly 4 working group, 4 report that has been released last year in 2020. So first, there was a working group on fatigue of hydraulic structures. So it was led by Dirk from the Netherlands. So technical report on the fatigue which occurs in any steel structure, but we wanted to go here to the specificity of the hydraulic structure. And for example, I know that was a major problems for the Panama lock gates, the design considering the fatigue assessments. Another working group on I would say advanced technology, if I can say, at least for hydraulic structure, is the use of the composite materials for hydraulic structure. So that working group will also present webinars in a few days. So please welcome to attend that presentation too. Another one with also a webinar, I think it's the 10th of December this year. It's about saltwater intrusion in the waterways. It was led by Tom from the Netherlands. So welcome for you if you have any interest on that topic to join the webinars. Now, a few words about some current working group. They started. I would say I will present you 4 or 5 working group. I would say it's not too late to join. Of course, it's time to join because they are running. So one is on the very important issue is the decarbonization of the inland waterway, and especially with regard to the infrastructure. That's one working group, which was led by Mark from TU Delft, but with the support of the CCNR and Pauli Gerno, sorry. 2 other one is the sustainable management of the navigability of free flow river. So of course, PIANC is basically interested by any type of waterway, not only on the canalized rivers, as we have most of the time in Europe, but also for the completely free flow river, typically what we have in South America. Another working group that has been launched, you see the date of launching. The first one was April, and the last one is just a few months ago, is the bottleneck and the best practice of transportation of container on inland waterway. So it's more technical economic working group. Then just launched yesterday, 23rd of November, handling accident and calamities in navigation of hydraulic structure. So countries like France, Germany, Belgium, Netherlands, this summer we had, I would say, calamities. So how can we manage that? And that is a working group where we'll present some recommendation about that issue. So welcome if you are interested to join. And we are preparing a new working group, probably launch it early next year. And that's it for the problematic of the floating houses that you find along all the big rivers. If you go to cities like Amsterdam, Paris, even in small city like in Liège, so all the quay now are used as permanent floating houses, and that create some problems for the river management, but also some issue related to flood and so on. So you are welcome to discuss with us on this issue. So I will finish by an invitation for next year's. This is the Smart River Conference, which is one of the big issue for PIANC, one of the big conference. It will be organized in China. It will be, I would say, organized a combined organization, of course, of attendance on the site. This is what we expect, but due to COVID, we will probably open the major part of the conference also to some remote event. But anyway, it's time that you take your pen or your computer to submit abstract. So the call of abstract is for end of December. We will accept your paper in January, but it's time. So now it's time for me to conclude and to thank you for all of you, the working group, and also all the participants. But it's not finished. I will give back the floor to Nick. So maybe some of you have more questions.
Thank you, Philip. We have no more questions that have come through on the chat, I don't believe.
I have a comment, if you allow me. When I saw the presentation of Ian White, where he showed this project of a hydropower plant, it seems that is not a navigable river. And he said that the difficulty, of course, or the cost is to make the connection with the electrical network, and that could be very expensive. So I think we have to split a little bit the problematic of installing hydropower, I would say, on river, but which are not navigables, and of course on navigable river. So I think most of the navigable river have time to times at least a connection with the electric network. So I don't think it's really an issue.
Nick, if I may just answer that. The site that I showed the photograph of, Philippe, is on a loop. And in fact, the navigation goes west to east across the top where there are several locks. So yes, that bit of the river for about 3 or 4 kilometers is not the main navigation, but boats can get down it. But the main route is through a canal. And it's one of those sort of schemes that Sebastian was describing earlier on. One of the issues is, yes, some of the locks, but it's where you've got a big navigation, you've got a lock, and it may well already have an electricity connection to it. But the question is the electricity connection suitable for the export of power? As some sites only have a single phase supply to the site, and generally you've got to have a 3-phase output supply. And for that matter, is the switchgear along the route man enough to cope with, say, 500 kilowatts certainly being injected to it? So the local grid operators are very keen on this. There's one site that Austin and I know that when the plant was switched on and started generating, it actually started to blow up the underground cables. It was causing all the joints in the cables to fail because the network was not capable of handling this kind of exported power being transmitted along it. So, and again, the grid operators are not always that keen about having local generating plants embedded in the grid. And my own personal view is that sometimes they try and prevent this happening by having quite significant connection fees. But there are new regulations have come in with the UK, because one of the problems we've had is what I call the domino effect, that if you have a lot of generators connected up and the voltage specification it loses its frequency or it goes outside of its permitted voltage range, can cause other generating plants to shut down, and then you get a major regional blackout. So that is also an issue that they're having to cope with in terms of the engineering of the network and the specific design of the switchgear for the hydro plants.
I think I would just add to that, Ian, that I think like the regulations for building a hydro plant in any particular country, the connection to the grid is very much site specific, and every site is different and every connection is different. And I know that some of the larger sites in Europe, they do have big connections because they have a lot of plant and equipment there, and so it might not be as difficult to connect up to them. And a lot of the major waterways in Europe run through large industrial areas. But I think also the same issue occurred in France on the Meuse River, because a lot of that area is now very, very rural, and there isn't quite the same heavy infrastructure of power generation and power transmission available in the more rural areas. So it is very much site specific, and you have to examine in detail the electrical connections. I'm working on an electrical connection at the moment, which is the other way around, where I'm trying to get a supply for about a pumping station that's about 1.5 megawatts in capacity, and that's not easy either. It's connecting to electrical systems is generally not an easy thing to do, and you should never underestimate the complexities of doing that. Okay, Philip.
Yes. I was not aware, Ian, but I understand now the situation. Thank you for your reply.
I'm just wondering whether we are ready to close the webinar, or do we want to wait a little longer? Or
I think so. Okay, maybe we can launch the last call to the participant. If they have any comment, please do it. Just to stay 1 minute more alive, if I can say, I may ask to the committee what they think. It's a little bit as Ian White suggests. There are also now some new, I would say, technology which are coming. For example, the rubber wares, but also there are the possibility to build a structure using floating units, a little bit like on the upper Meuse. So you avoid to have expensive civil engineering work, which are rather expensive and make the investment cost important for hydropower station, for small hydropower station. So I think of using the waterway or in order to transport the materials, and using this, I would say, light technology as rubberware or floating structure, even floating floors. We may make the hydropower plant, small hydropower plant, more attractive and more economically efficient. That's a point of view. So I don't know if you want to react on that.
I think there are some examples of in Belgium of power plants. I think Sebastian presented one, but there are other examples where the power plant is located downstream of an existing either fixed or active weir, and the power plant is moved out of the way to pass floods. So that removes the need to dig another channel to install the hydropower plant around a weir. But that does present its own complications. You have to make the whole power plant movable in some way, whether it moves vertically or sideways. But those approaches have been used very successfully in Belgium. And one of the members of the team that did that work was also on the working group. We did actually visit a place in Holland where they had floating little floating power plants, which sort of had a water wheel in between them, and they were mainly extracting energy as the water flowed under the floating structure rather than a conventional hydropower. But the outputs were kilowatt size, and you'd need a lot of them floating on the surface of the water to extract any meaningful amount of energy. So we restricted our approach or our work to what was available on commercial and industrial size in terms of hydropower technology. But you're quite right, Philip, there are developments coming down the road which may make things better and more economical. Certainly the biggest advance that I came across in looking at it, apart from movable power stations, was the Vlh turbine, the very low head Francis turbine. Sorry, yeah, Vlh turbine, which was the one thing for development specifically targeting this area of work. So and there's some good innovations in the way that's put together, and minimizing civil works and maximizing maintenance opportunities.
Thank you. So I think you may conclude, Nick, if there is no other question.
Yeah, I just want to say thank you very much on behalf of WG 197. We had it was an enjoyable experience putting together the reports, seeing some innovations, seeing how some navigation operators have already developed hydro plants and how ingenious they've been, both technically and commercially and regulatory. It's been a good experience. We should have presented this a little bit sooner, but we have had a pandemic that's sort of made us struggle for the last 18 months. I think using a webinar such as this is a good way to disseminate information and it's certainly helped us to get our guide out there and noticed. So thank you very much to all members of WG197, and also to you, Philip, as the chairman of InCom, for instituting it and giving us a chance to put together the report. Thank you very much.